This is the 12th video in this series. And if you've seen the previous videos and you've looked at the thumbnail for this video, your immediate question might be, what's going to be the difference between a list and an array? Isn't that basically the same thing? Well, in this video, I'm going to try to address an issue with the implementation of lists in Funciton, and hopefully that will enable new and exciting possibilities in the future. So here's the thing that has always bothered me about lists in Funciton. You see, if you want to get to, let's say, the 10th element in a list, you always have to decode the previous 10 elements first. You can't just jump to the middle of a list. Now, all of you who are programmers know that in a normal array, in a normal programming language, you can always just index anywhere inside the array. And this ability to index into an array is used with great effectiveness to create more complicated data structures that enable algorithms with reasonable performance. One such algorithm that you may have heard of is binary search. For those of you who don't know what binary search is, here is a very quick summary. The idea is, let's say you have an array in which your elements are already in sorted order. So for example, this 5-element array here, consisting of 12, 22, 47, 61, and 89, let's say we want to find out where in that array the number 61 is. If this were a list, then you would just have to decode the first element, and notice that it's not a 61, and then the second element, check if it's 61, and you would have to keep going until you reach either the element 61 or the end of the list. But as soon as you have the ability to jump into the middle of the array and just index into it at any position, suddenly you can do the following. You can take a look at the middle element, which in this case is 47, and then, because we assume that the array is sorted, we notice that 47 is smaller than the 61 that we're looking for, and so all of the entire first half of the array we can already ignore. So now we only need to look at the second half of the array, and now we can just jump to the middle of that. Now in this example it's the next element, but if you had a really large array with hundreds of elements, then this would allow you to cut it into half over and over again, which means that you can home into the element that you're looking for using a number of steps that is only the logarithm of the number of elements in the array rather than the number of elements, because you have to go through every one. So the main goal of this video is to implement something that will allow us to do binary search. So how are we going to encode an array in a single integer? We mustn't lose sight of the fact that we still want to accommodate arbitrary size integers. So if you want to come up with a system that can do this, feel free to pause the video here. Otherwise, I'll jump right into explaining what my idea is. Well, in the lists video, I made the following fallacious assumption. I said that because we wanted to accommodate arbitrary size integers, that we absolutely needed a variable length encoding, because if we limit ourselves to a specific maximum number of bits per element, then we wouldn't be able to represent numbers bigger than that. But consider any array of elements, there will be one number in it that is the largest, and we can just count how many bits that largest number has, and then we can pad all the other elements to that same number of bits. And now if we concatenate them all up, we can always retrieve each element because we know exactly where they are, as long as we know the number of bits per element. So the challenge really only boils down to, how do you represent an arbitrarily large number of bits per element? And the answer to that is, we already have a variable length encoding, which we are using for lists, and as I hinted in the lists video, you can also use it for tuples. So I'm going to use a tuple for this. The first element in the tuple is the number of bits per element, and the other element is literally just all of the numbers concatenated. And crucially, only the first element in the tuple, which would be the bit length here, uses the variable length encoding. The rest of the number is just right there, which means that we don't need a loop to decode that. So we can always retrieve the bit length using the shift function, and then we can just index straight into that block of bits. Similarly, if we want to add a new element to an array, since we know exactly where every element starts, we can always shift the bits after that a bit forward, creating a little gap, and then we can slot the new number into that gap. Sounds reasonably simple, right? Well, I've thought this through, and I've identified 6 special cases that need to be taken care of to make this work. If you want a challenge, Pause the video here and see if you can list all 6 of them. Issue number 1. What if the number we want to insert is too large to fit in the gap? So let's say our array currently uses 5 bits per element, which means that the largest number that you could accommodate is 31. What if I want to put a 77 in there? The solution to that is going to be that we're actually going to re-encode the entire array to make the slots bigger. My hope is that that will happen rarely enough to not impact performance too much. After all, we will never do the opposite. We will never shrink the array again. So once the slots are large enough to accommodate the numbers that we want, we won't need to keep doing that. Issue number 2. What if the number that I want to insert is negative? See, now we're conceptually dealing with a number that has infinitely many leading 1s instead of leading 0s. So no matter how large we make the slots, it's just never gonna fit in there. The solution to that is that we're going to allocate a single bit as a sign bit. And I'm going to put that sign bit first before the element. And if the element was a negative number, then I will store the bitwise negation of the number, because that will guarantee that it has a finite number of bits. Issue number 3. What if we are inserting an element at the end of the array, and that element that we want to insert happens to be 0? Well, now the sign bit is going to be 0 and the number is going to be 0, which means that we're not actually going to change the array at all. So how will our functions know that there is an extra 0 at the end of the array? The way that I've decided to implement this is by having the count, as in the length of the array, the number of elements in the array, encoded at the start of the array. And the number of bits that we use for that is the same as the number of bits that we use for each element, except that the count doesn't need a sign bit, because it's always non-negative. Issue number 4. What should happen if we try to insert an element beyond the end of the array? In other words, an index that is greater than the length of the array. You see, if we naively just increment the count each time, then we would actually end up adding a 0 element, and then we would also be putting some extra bits beyond the end of the array which would never be read, because the number of elements never includes it. Now, the way I've decided to deal with this situation is that I'm actually just going to make the array larger. So if you start with an array with just 1 element, and then you insert an element at index 10, it should return an array with 11 elements, and the intervening elements are all going to be 0. Issue number 5. What if the index at which we're trying to insert an element is negative? Well, this is the only one that I've decided not to address. If the user specifies a negative index, then they've done something wrong. There is a bug somewhere else in the code. So just don't pass in a negative index. And finally, the 6th special case is, what if the array is empty to begin with? So far, with lists and lazy sequences, and even strings, we've always maintained this convention that if it's empty, it's represented by the number 0. I want to continue that tradition so that I can always check if an array is empty just by checking if it's 0. But now you might reasonably ask, what if I encode an array where the count of elements that is at the start of the array is 0? Wouldn't that represent an empty array as well, despite the encoding not being 0? Well, here's how I've decided to address this. I'm going to make it so that this block that encodes the number of elements in the array is actually off by 1. In other words, if the array has 5 elements, I'm just going to put a 4 in there. And that means that if the array has only 1 element, then this number will be 0. So you can't actually set the number to 0 to represent an empty array. And that means that all of our functions that remove elements from an array will have to check if that makes the array empty, and if so, return 0. Okay, enough talk. We've talked about what the encoding of an array should look like. Now let's write some code that will actually do it. And this is going to be a very low-level function, which is going to assume that some of the work has already been done. So I'm going to write a function that will take 3 pieces of information, which I'm going to call B, C, and D, where B is the bit length of each individual element, including the sign bit. C is the count, or the length of the array, the number of elements in it. And then D is what I will call the data block, which contains the rest of the array, with the count taken out. So it's literally all of the elements in the array concatenated, but with the sign bits still there. So how do we create a valid array encoding for this? Well, first of all, what if the count is 0? Well, if the count is 0, then the array is empty, and we've agreed that we're going to represent an empty array as the number 0. So let's check for a 0 count and return 0 if that is the case. Now, if the count is not 0, then we want to use the unshift function from our lists video in order to create the tuple, where the first element is the bit length. Now, I don't quite remember the order of the arguments here, so let's take a quick look at the lists library. And here you can see the comment that documents the unshift function. And you can see that I actually got it wrong. The new element that we want to add on should go on the left here. So b should be here. But what should the other value be? In the documentation we said list, but this is assuming that you're adding an element to a list. Whereas what we're doing is we're using this as a tuple. So we need to tack the count in front of the data block. So we need to shift left the data block by some amount in order to make a gap. And we've decided that we're going to use b number of bits to accommodate the count. So we want to do this, and then we want to bitwise OR this with c in order to put that value in there. Well, except that remember we said that we're going to store 1 less than the count, so we actually need to decrement that. So let's start by writing the bitwise OR. Then let's put the decremented c on one side, and then we can immediately connect up the c's. Now let's write the shift left, and then we only need one wire crossing function, and we can put the declaration box at the top. Now, I fully expect that this function is only going to be used internally by the array library that we're about to write, so I'm going to mark this function as private, but even so, let's put a comment on it to document what the 3 parameters are that it needs. And with that, we've written our first function for our new library. Now, I said I was going to make the function private, but actually I'm going to go back on that for now, because I want to be able to test the function. So let's start by just calling that function with 3 values, and let's convert the output to a string so that we can see the numerical value. Okay, let's construct an array with 1 element, and for the data block I'm going to put a 6. Now 6 in binary is 1, 1, 0, which means that this will be interpreted as a sign bit of 0 and the number 1, 1, which is 3. So that means we need 3 bits to accommodate that number, so I'm going to make this a 3, and then let's see what happens if we run this. And we get this value, which we can convert from decimal to binary, and we get this. Okay, now if you remember the list encoding, you'll know that this is the sign bit for the first element, which is always going to be 0 because our bit length is never going to be negative. Then we have the continuation bit, which says that there's going to be a 21-bit chunk to encode at least part of the number. And then these are the 21 bits, which do encode the number 3. And then we have the stop bit, which says that there are no further chunks. And then the rest of this is the raw array. You can see that there are 3 zeros. Now that is wrong, because the length of the array is oh, no, it's not wrong. The length is supposed to be 1, and it's supposed to be stored as 1 less than that. So we do actually get a 0, and then here we have the 0, which is the sign bit, and then the 1, 1, so this should be an array containing the number 3. Now, just to make sure that this wasn't a bug, that I got 0, let's put a 2 here, which means that now the array will contain the number 3, which is encoded by the 6, and then the number 0. So let's see what that looks like. And it looks like this. So let's convert that to binary. And you can see that the only difference is this extra bit. So now the 3 bits that encode the length of the array say 1, which means that the length is actually 2. So that seems to be working. So now that we have what I think is a valid array, let's see if we can write a function that will retrieve a number from that array. So this time let me write the test program first to demonstrate how it's supposed to work. So in this example, I'm passing the array as the first parameter and then 0 as an index. So I expect this to give us the number 3. So once again, let's start with checking if the array is empty, and if it is, then we just return 0. But if the array is not empty, well then we need to obtain those 3 values, the b, c, and the d, right? We need to know the bit length in order to know which bits from the data block to extract. So I'm gonna have to write that first. Now this time we're dealing with a function with 3 outputs, which we can do as long as we have only 1 input, which we do. Now once again, if the array is empty, in other words 0, then what do we want these outputs to be? Well, we definitely want the count to be 0, and honestly the only sensible thing for the others is to also return 0. So let's just do that. Let's return 0 for all 3 values if the array is empty. Now let's go them in order. The first one that we want to come out, which is this one, needs to be the bit length, which we obtain by using the shift function to deconstruct that tuple. And once again, I don't quite remember what the order of the arguments on this is. So let's look at the library again. Let's scroll down to the shift function. And it turns out that the list, or in our case the tuple, goes in at the top, and then the first thing that comes out is the tail, which in our case contains both the count and the data block, and the head is the bit length. So we need to rearrange this so that the outputs are left and right, and then we only need to pass the array into here, and then the first thing that comes out is the block containing the count and the data block, and the other part is the bit length, which we do want to pass into here. Now the next thing that we want to return from here is the count. But how do we get the count from the block of bits that we get here? For that, we need to know the bit length, so we need to take a copy of that. Now the actual count is 1 more than the value that we have in our block, so we need the increment function. Now, how do we actually get the value that we need to increment? Well, it's the bottom b bits of whatever comes out of here. So to extract those bottom bits, we need a bitwise AND. Now, one side of that bitwise AND is literally just the block that comes out of here. So let's just join that up directly. Now, on the other side of our AND, we need a number that consists of b 1 bits. Do you remember the formula for that? Well, the formula that I've always used is -1, shift left the number of bits, and then a bitwise negation of that. Because -1 starts with all 1 bits, and then shifting that left by b creates b 0 bits, and everything else is 1. And then the negation will create b 1 bits, and everything else is 0. So we need a bitwise negation, a shift left, and a -1 box. Now finally, how do we get the data block which we want to return from here? Well, that data block is the rest of the bits from this value. So we're gonna need to take a copy of that as well. And since the bottom b bits of the block constitute our count, which we're returning here, we just need to shift those out in order to get the rest of the block which we want to pass here. So let's put a shift right function here. Now we want to take the block and shift it right by b, and we also need a b over here. So I think I'm just going to join those two up. And now we can join up that b and pass the block through a y-crossing function. And finally, we just need to join up all the a's. And of course we want to document this function in a comment as well. And with that, we have the second function in our library. So I want to test this function as well. So let's call the function. Now let's start by testing the first output, so I'm just going to silence the other two. And now I expect this to be the first output, which is the bit length, which should be 3. So let's see if that's what we get. And we do get a 3. Now let's silence that one and activate the second one. So now we expect the second output, which should be the number of elements in the array, which should be a 2. So let's see if that's what we get. And indeed we get a 2. And finally let's activate the third output. And now I expect that to be a 6. So let's see if that's what we get. And indeed we get a 6. So we now have these two complementary functions, one for encoding and one for decoding. So let's go back to our indexing function. We have an array to index into and an index. But we need to turn that array into those 3 parts. So I'm going to draw the declaration box and the decode function to obtain those 3 items. And now we have b, which is the bit length, c, which is the count, and d, which is the data block. So we might be tempted to do some bit shifting on the data block in order to retrieve that one element. But here's the thing, we probably need to do that in other functions as well in the future. So I think I'm going to make myself another helper function. Specifically, I want to pass the bit length, the data block, and the index, because that's all I need in order to extract one element. And so I can just have a 3 input 1 output function to do exactly that. This time let me start by drawing the declaration box. Now we definitely need to shift the data block to the right. But by how much? Well, we know that we want to get rid of the first I elements, because the element at index I is the one that has I elements before it. And each element has b number of bits. So it's b times I. Now we're not going to need the index again, so we can join that up immediately. Now that we've shifted it right, we now need to extract the next b number of bits. We should do that the same way that we extracted the count in our decode function. So we need a bitwise and we need to AND with a number that consists of B1 bits. So let's apply the same formula that we did before. And now just join up the B and we're done. Once again, let's document this function with a comment. Now, this function is not complete, and you'll see in a second why. Now, in order to test this function, I'm just going to pass the values in directly instead of trying to construct an array first. So let's pretend our bit length is 3 as it was before. Let's say the data block is the 6, the same 6 that we had earlier. But now we want to retrieve the element at index 0. And then of course we want to turn that into a string for output. Let's see what we get this time, and we get the number 6. But that's not really what we wanted, is it? I mean, 6 is the raw encoding of our element, but remember that the lowest bit is actually a sign bit. We expected the number 3. So the value that comes out at the bottom here needs to be decoded. So ultimately we need to check the bottom bit, so let's use a question mark for that. Now, if the bottom bit is 1, then we actually want to return the bitwise negation of the number. And the number that I mean is the rest of the bits, with the first bit removed. So we need to shift right by 1, but I'm going to write that as shift left -1 as usual. Now, how do we obtain the bottom bit? We do that by doing a bitwise AND with 1. Now let's see what we get if we run that same program. I expect this to give us a 3 now. And that seems to work, but now what if instead of a 6 this were a 7? That's basically the same number but with the sign bit set. So we expect the bitwise negation of 3, which is -4, and there it is. We should now have everything we need to finish our indexing function. We want the result of it to just be an invocation of that extraction function we just wrote. And the order in which it expects the arguments is the bit length first, then the data block, and then the index. Crucially, you will have noticed that we don't actually need the count. If the index that the user provides is outside the bounds of the array, then this will automatically just return 0. So let's silence the count output. Now we can easily join up the D's, but now it becomes apparent that we still need a copy of A, which is the value that comes out of the declaration box here. So we need to take a copy of it. And now I see that I should have put this wire crossing function up here. So let's move it there and connect up the B's. And finally, connect up the index. Now, I originally chose this character because it's an open square bracket with a line, but it looks a little bit too much like a capital E, so I think I'm going to change it. Alright, let's round this off with a comment. And with that, we already have 4 functions in our library. Oh wait, this is wrong. This should be a left arrow. So back to our test program, I'm going to press undo to retrieve the part of the program that constructs the array. And now we're going to use that index function on it. So let's start by retrieving element number 0, which we now expect to be 3. Let's run that, and we do get a 3. And once again, if I change that 6 to a 7, I now expect that 3 to be a -4, and it is. Now, what happens if I turn this into an 8? 8 in binary is 1, 0, 0, 0. And remember, we're using 3 bits per element, which means that the bottom 3 bits will now be the first element. So the first element should now give us 0, and it does. But now if we look at the next element, element number 1, well, we now have a single bit, which is the sign bit. So I expect this to be -1, and it is. Perfect. That seems to be working. Now, except for the encode function, everything we've done so far is retrieving elements from an array. Now, let's start putting elements into an array. So I want to create an insert function, which will take an array that we want to insert into, an index at which we want to insert, so everything after that index will shift forward, and then the element that we want to insert at that position. Now, this is the point where the 6 special cases come into play that we talked about earlier, so we need to make sure that we take care of all of them. And this is what those 6 conditions were. Obviously, we don't need to do them in this order. In fact, I think I'm going to start with this one. What if the array is empty? So let's start by drawing the question mark box to check if the array is empty. Now, if the array is indeed empty, I want to use that encoding function that we wrote earlier to create an array out of whole cloth that has that element at that index and everything else is 0. So let's invoke that function right here. Now, the 3 parameters that this takes is the bit length, the number of elements in the array and the data block. Now, since we're placing an element at an index I, and I'm going to assume that index is not negative, what will be the length of the array after that? Well, the answer is I plus 1. Because if you put an element at, let's say, index 5, then you'll have 5 zeros before it, so you end up with 6 elements. So we need the increment of the index. But what is the bit length going to be? Since our input array was empty, we don't have a bit length to work with yet. So we need to work out what the bit length is that we need to accommodate the element. So we're going to need a function to figure out the bit length of any element. Now, fortunately, this is not hard. If the number is 0, then the number of bits is 0. Otherwise, we increment the result of a recursive call, and the recursive call is going to receive the number shifted right by 1. So we're going to be chopping off 1 bit at a time. And now just add the declaration box, and let's also document what this function does. Now let's quickly test that function as well. So this time all I need to do is just call that function with literally any number. So let's try this on the number 2, and I expect to see a 2 because 2 in binary is 1, 0, which is 2 bits. Now what about the number 7? That is 1, 1, 1. So we should be getting a 3, and we do. And then one more than that should be an additional digit, so we should be getting a 4. That seems to be working. So now we know how to obtain B. But how do we construct D? Remember that the number that we're encoding could be negative, which means that our D, which is the data block, needs to contain the number with the sign bit. So I think we should quickly write a helper function for that as well, which will just add the sign bit and negate the number if it's negative. So for this one, we need to check if the number is negative, which we can do with the interrobang function. Now, if the value is indeed negative, then we need to bitwise negate it. And then we need to shift it left by 1 in order to make space for the sign bit. Okay, but now we need to set that sign bit to 1 if the number was negative, which means that we need to reuse this condition. So in the case that the number was negative, we need to do a bitwise OR with 1. But we don't need to get Funciton to calculate the negation of 1. We can just do that ourselves. It's negative 2. And now we just need to join up that condition. And now let's move that less than to the top and add a declaration box. And once again, I want to document this function with a comment. And just like that, our library keeps growing. So once again, let's quickly test this by simply replacing this with the new function. Now, if I were to encode the number 8, I expect the result to be 8 with an extra 0 bit, which is of course 16. And it looks like that is what we get. But if we have a negative number, let's say negative 8, then that number should be negated, which gives us 7, and then have an extra 1 bit added at the end, which would give us 15. Now, the number 0 should give us 0, which it does, and negative 1 should consist only of the sign bit, so that should give us 1, and it does. Now, confident that that function is working, let's go back to the insert function that we've been working on the whole time. We now know that we need to use the function that counts bits on the encoded form of our element. So what comes out of here is the bit length that we need, which we need to pass into here, but we also need it to construct the D. So what we want to do here is to shift left the encoded value. So let's put a shift left here. The thing that we want to shift is the encoded form of the element, which is the thing that comes out of here. So we need a copy of that. Let's call that EE for encoded element. Now, how many bits do we want to shift that left by? Well, we want to place our element at the index I, and we know that each element has B bits, so it's B times I, isn't it? Now, I'm going to put the B on the top of the multiplication and the I on the bottom, because then I can connect up the B's quite easily with just one Y crossing function for the A. And we can connect up the encoded element, the double E, as well. Okay, that is the first, or rather the last in this list, of the special conditions that we need to take care of. So I'm going to remove that. And I'm also going to remove this one, because we said that if the index is negative, we're just going to ignore that. We expect the caller to be careful with that. We've also basically already solved the zeros at end thing, because we're using that encode function, remember, the one that includes the count. So we can get rid of that as well. And similarly with negative numbers, well, we're now using this encoding function, which will take care of the sign bit. So we can get rid of that as well. Now the rest of our function needs to go into this part of the question mark. So let me quickly rearrange things so that I can actually put stuff there. And now we need to take care of this. What if the number is too large to fit in the gap? In that situation, we need to re-encode the entire array. Now, what do we need to pass in here? Wait, there's an unlabeled edge here. This is the element. So I'm just going to put an E there. So what do we need to put in here? Now, no matter what happens, even if one of the other special cases is the case, we definitely want to return an encoded array. So we want to call this function here as well. But I'm making it separate from this one because our arguments here are probably going to be very different. Now the first thing that we want to pass in here is a bit length. But remember, this might not be the bit length of the original array because we might have to increase it if the number is too large to fit in the gap. So I'm going to call this b prime because it might be a modified value of b. The next thing we want here is the new number of elements in the array. Now let's think about what that should be. If we are inserting into the array at an index that is already within the array, well, then it's going to be one more than the previous count. But what if our index is bigger than the length of the array? We want to pretend like we're adding zeros in between. So let's say we have a 5-length array and we're inserting at index 10. Inserting at index 10 means that element will become the 11th element. So in that case, we actually want one more than the index. So either way, we want to increment something here. So let's just put the increment function right here. And then the third argument here is going to be the new data block. Now that is going to entail a lot of calculation. So I'm just going to put d prime here for now for the new data block. Let me quickly rearrange a few things to make more space for that d prime. Alright, now let's think about what our d prime wants to be. Let's assume that we already have b, c, and d for a hypothetical array where the element does fit. In other words, let's assume that we've already fixed the bit length so it can accommodate the new item, and the data block has already been re-encoded so that all of the elements actually have the new bit length now. We're going to take that data block, we're going to shift it right all the way so that the place where we want to insert the new element is at the start. Then we're going to shift it left by the number of bits that we need. Then we're going to insert the new element there using a bitwise OR. And then we're going to shift it all the way back. And finally, we need to put the earlier part of that block back in place, which we do with the bitwise OR as well. So how are we going to do that in code? We want to take our data block and shift it right so that the part where we want to insert is at the start. So there are I number of elements before that, and each element has b number of bits. Then we're going to shift it left to make space for one element, so it's just b number of bits. Then we're going to use a bitwise OR to put the element in, except this is not the element that was passed in, because that one could be negative. So we need the encoded element, which I'm going to call EE. And then we want to shift it all back to the left. Now we want to shift it by the same amount that we shifted this, which is I times b. But I don't want to do the multiplication twice. So I'm going to introduce j. And I'm going to say that j is equal to I times b. So I can just use j here as well. We've now effectively killed the first I elements in this data block. So we need to put them back in, which we do with the bitwise OR. But now we need to extract only those bits for those first few elements. Well, extracting bits we know how to do. We just bitwise AND with the same formula as before. But now how many bits do we actually want to extract? Well, once again, it's going to be j because it's the I first elements. So that completes the formula. But remember that we've pretended that we already have the new bit length and data block. I previously called that b prime here, but I now think that we don't actually need the original bit length. So I'm just going to call it b. And the same with d. I'm going to say that this is the data block after recoding. But of course what we need to put in here is the result of this. So I'm going to call that b prime. Okay, so at this point we've taken care of all of these special cases, so I'm going to remove this. And now let's translate that monstrosity of an equation into Funciton. We need to start with a bitwise OR, so let's put that here. Now both of the operands of the OR are going to involve a shift left at some point, but this one here does an AND first, and we express AND as NAND followed by a bitwise NOT, which means that we can cancel it out with one of these bitwise NOTs. So let's start by transforming this into a bitwise AND, and let's move everything far enough to the left to fit in the shift left. Now that E here is kind of in the way, so let me angle that over to make some space. Okay, so the -1 shift left needs to have J as its second argument, so that goes here, and this needs to join up. Now in order to fit that rest of the equation over here, I'm definitely going to need a lot more space on the left, so let me move everything over. Now on this side of the OR, we want to do a shift left J. And the thing on the other side of that shift left is another bitwise OR. Now one of the operands to that OR is that double E, which is the same thing that comes out of this box here, the encoded element. So I'm going to reuse that. The other side of that OR, well, we need to do this in the right order, so the top level operation is a shift left. And the thing that we want to shift left is this, and we want to shift it left by B. So that leaves us with a shift right. So translation of this to Funciton is complete, so I can get rid of that. Now I want to quickly rejiggle this so that the J points up and it can more easily connect with the other J that's right up there. Now we can connect up the J's, and remember it's I times B. So I'm quickly going to put the multiplication right there. Now I can put the I and the B on either side. So I'm just going to put IB here for now, and I'll decide later which should go where. Now we need to think about where that B and the D come from. This whole time we've assumed that the B and the D are already big enough to accommodate the new element. So we need to make sure that they are. And I think that would be easiest to do with a separate function. After all, if we're going to re-encode all of the elements, we're gonna need a loop for that. So we're gonna need a helper function anyway. So now I want to write a method which will take an array, let's call it A, and it will take a value, and it will check whether that value will fit into the array. In other words, whether the bit length of that array is sufficient to accommodate the value. And if it isn't, it will re-encode the entire array to make it fit. So the first thing the function needs to do is to check whether it fits, and if it does, we can literally return the same array that we were given. But how do we determine if the value fits? You know, I just realized I should be consistent. I called this EE before for encoded element, so I'm going to stick to that nomenclature. So, if we take the encoded element and we shift it right by the previous bit length that the array currently has, well, if that gives us 0, then it means that all of the bits in that encoded element did fit, which means that we can just reuse the array. So let's put a shift right here. Now, if we do need to re-encode the array, then we certainly want to end up with a fully constructed array. So I'm going to put the encoding function right here. Now that encoding function is going to need to know the new bit length, which I'm going to call B prime. The new number of elements in the array, well, that one doesn't change, so I'm going to call it C. And then we need the new data block, which does change, so let's call that D prime. But that new data block is definitely going to be calculated by a loop. So I think I'm going to put a call to that private function right here. And this helper function is going to need 3 parameters. First of all, it's going to need the original data block, the one that we're changing. It needs to know what the previous bit length was, so it knows how to chunk it up into the individual elements. And then we need to know the new bit length, which is B prime. So let's quickly write that function down here. So if D, the data block that we're dealing with, is 0, then we don't need to do any more conversion, even if the rest of the elements are all 0. So if D is 0, then the result is going to be 0. If D is not equal to 0, then we need to extract the first element from the data block. Then we need to do the recursive call in order to encode all the rest of them. And then we need to put the new element back. So we're going to have a recursive call with the data block, but with one element removed, which is shift right B, because remember B is the original bit length before conversion. But we need to pass the B and the B prime into the recursive call as well. So once the recursive call comes back, we can now shift the result left by b prime, and that will give us a gap of exactly the size that we need in order to put in the element that we removed. So we need to use a bitwise OR and then extract the element. Now the element is of course at the start of D, so we're going to need to use D, and then we need to mask out just that element. And once again, masking is done by bitwise AND with a bitwise NOT of -1 shift left number of bits, which is B. So our helper function has a question mark on the top level, so let's start by writing that. And if D is 0, then the result is 0. Otherwise, we need to do that bitwise OR. Now, one side of that bitwise OR is going to entail this recursive call. So I think I'm going to put that one on the right. So let me just quickly swap these two so that this is less confusing. Now on the top level here we have a shift left, so let's put a call to the shift left function here. The second operand is b prime, but the other operand is the recursive call. So let's put a call to that right here. In order, the arguments are d shift right b, and then b prime. And we can put the shift right box right here. On the other side of that bitwise OR, we have a bitwise AND. So the bitwise NOT is going to cancel out, so I'm just going to remove that. And then we're going to have an AND, which is now a NAND, with the usual formula for a number with b bits. And at this point everything is b's, d's, and b prime, so we should be able to join it all up with a declaration box. So far so good, so we can get rid of that formula. We have now obtained the new data block, but we can only do so if we know the new bit length. So we need to obtain that. And in order to calculate that, we need to know how many bits we need extra on top of the bit length that we already have. Now remember we did the shift right to find out whether the element fits. Now the thing is, if it doesn't fit, then the result of this will actually tell us how many extra bits we need to add. So let's take a copy of that calculation. And now, in order to determine how many extra bits there are, we can just determine the bit length of that number. And we already have a function for that. So now we know how many extra bits there are, that comes out of this function. We need to add that onto b in order to get b prime. And now that we have the b prime, we can join it up with all the places that need it. And now we need b, c, and d, which we can get by just decoding the array. Now to get that c in here, let's use a wire crossing function, and then we can put the b in all the places that need it. Now let me quickly compactify this by one line. And finally, let's put in the declaration box and join up the a's and the e's. So, if I haven't made a mistake, then that is a function to re-encode an array. So let's get rid of this, and let's write a comment to document what this function does. And that is already our 7th function for the library, 8th if you include the helper function. So let's go back to the test program that we had earlier, where I'm constructing an array which uses a bit length of 3. So now let's call our new function on that. You know what, let's first remind ourselves what the array actually looks like when encoded. So I'm going to start by just outputting this array in its raw form. And now if I just run this, I should get this number, which I can convert from base 10 to base 2 to get the binary representation. And as we've discussed before, we have a sign bit and a continuation bit. Then this is the number 3, but stretched to 21 bits. And then this is the stop bit, which means that this is the count, the number of elements, but reduced by 1, so we have 2 elements, and then this is our first element, which is the number 3, but 6 when encoded. So now let's modify this program by calling the function that we just wrote. And let's give it a new value that uses more than 3 bits, for example 8, which requires 4 bits. And then of course we need to convert the result to a string for output. And see what happens if I run this. Now I get a very different number, so let's see what happens if I convert that to binary. At first glance this looks like it worked fine. We have the sign bit and continuation bit, and now instead of the number 3, we have the number 4, stretched out to 21 bits. Then we have the stop bit, and then the count hasn't changed, but it is now 1 bit longer. So this is the count, and it means there is 1 plus 1, so 2 elements in the array, and then we have the 6, which also hasn't changed. So that seems to be working perfectly. Now, are we ever going to finish this insert function? Jesus. Well, we now need to obtain the B and the D for the re-encoded array. So we need to re-encode the array at some point. So we have our original array, and then we need to pass in the encoded form of the new element, so not E, and that encoded form is already being calculated down here. So I think I'm just going to take a copy of that right now. After we re-encoded the array, we now need to turn that into a B and a D. Well, and a C, but we don't need the C. So we need to call the deconstruct function. So the order of outputs here is B, C, D, and we don't care about the C, so I'm quickly going to silence that. We can also get rid of this annotation here on the left, we don't need that anymore. And the only place where we need D is down here, so we only need one wire crossing function to make that work. And now, let me move this up a little bit more. We need to join this up with all of the places that require a B. Now, I almost completely neglected to figure out which one we need to put in here. It's either C or I, where C is the number of elements in the array, which doesn't change from the recoding, and I is the parameter that is passed in. So let's think about which one we want. Well, if the index is within the array, in other words, less than C, then we want to increment the count, because we're just adding one element somewhere. But if the index is beyond the end of the array, then we're adding that element like way off to the right, and we're pretending like we're adding 0 elements in between. So this actually needs to be a question mark, and the condition on that question mark, which comes here, is whether the index is greater than the count. And that's a boolean, so we can use the interrobang function here. Now, if the index is indeed greater than the count, then we want to use the index, and in all other cases, we want to use the original count. Now, if I connect the i's here, then the C will be trapped. So I'm actually going to change this to less than or equal to, so that I can swap this around. So let's write the less than or equal to. Then we can connect up the C's, and then let's think about how we actually get the C. You see, we've been using this array decode function after we've recoded the array. Wait. Oh, I forgot something. We're using the recoding function to make sure that we can accommodate the element. But what if increasing the count is the thing that takes us over the bit limit? Because, it could be that you have an array with like 4 elements, so the count number would be 3, which is just 2 bits. But what if all of your elements are only 2 bits, and then you add another element, right? You now have to increase the bit length just to accommodate the count. So it's not enough to just put the encoded element in here. We also have to take account of the new count. And the new count is what comes out of here. I mean, the actual new count is what comes out of here after the increment, but we all know that the encode function is going to decrement it. So the number of bits that we need to decide on is for what comes out of here. So we're going to need to take a copy of that here and then route it all the way around the function. Okay, but now what do we do with this? Because we're already passing the encoded element into here. Well, let's think about this. The function doesn't use the encoded element for any other purpose than to find out how many bits there are in it. So it's actually enough to pass in literally any value that has the number of bits that we need. So all we need to do is to combine that new count and the encoded element in such a way that we have enough bits. And the way to do that is with a bitwise OR. Okay, now we still need to obtain the original C. You see, we can't take the C from here because this call depends on this call, and this call depends on the new C, the new count, which in turn is calculated from the old count. So we actually need to run this function twice, once just to get the original count, and then the second time here. So let's quickly do that. And now I think it's time to zoom out so we can see the whole function. And we can now see that the only variables that we still need are A, I, and E, which are the parameters to this function. Now I think I want the declaration box at the top, so let me quickly draw that. And now I'm going to have to put a lot of wire crossing functions in to join everything up. This is quite a rat's nest, honestly. So, after all of that, we finally have what I think is a function to insert an element into an array. Let me quickly write a comment for this one. Okay, I think that looks pretty good. Assuming, of course, it works. So we should probably test that. So in our test program, let's use the insertion function here to insert an element, which almost doesn't matter what the element is. So let's use 0 for now, into this index. So let's start by inserting it at the start of the array, index 0. Now, since we're inserting a 0, this shouldn't require a recoding of the array. So the bit length should still be 3, as it was before. So let's run this and see what happens. We do get an answer. Whether that answer is correct remains to be seen. Alright, so we have a sign bit, a continuation bit, 21 bits encoding the number 3, which is the bit length. So that hasn't changed. So then we have the stop bit, and then every block of 3 bits is an element. Except that this one here is the count. We started out with a count of 2, so now the count is 3, but this is 1 less, so that's a 2. That's correct. And then after that, we have the number 3. Remember, this is the sign bit and this, so that makes a 3. But we expected this to be 0. And then we get another 3 there. Well, this is curious. Why are we getting a copy of that? So there's definitely a bug in the function. So let's try and see what happens if I insert R0 at position 1 instead. So let's run that again. We get a different number. No, we actually get exactly the same number. Interesting. Did you spot my mistake? You may remember that we're using a bitwise AND here to extract the lowest I elements from the array in order to put them back in after we've shifted the rest of the array. And there is a crucial part of the formula missing here. Can you see it? Well, the answer is a bitwise not. We need to shift left the -1 by a certain amount, and then we need to negate it in order to get the 1 bits that we want. So let me quickly fix that. And then we go for attempt number 2. Let's run that program. And we get... that number looks different from what we had last time. So let's convert that into binary. And let's take a look at this. So we have the 3 with the 21 bits and then the stop bit, which means that this is now the size of the array, which is 2, which is 1 less than 3. So that's correct. And then we have the 0 that we inserted. And then we have the 3 that was already in there. Now, if I insert the number 2 instead of 0, I should get a slightly different number. Let's see what it looks like when I convert it. So I assume that this is the 21 bits and that is the stop bit. And this is the count of the array. So it's size 3. It's the same as it was here, so that's correct. But then for some reason, we have the 3. Yeah, I expected to have the 2 first and then the 3. So somehow the 2 just disappeared. Did you figure out what's going on here? What's going on is that I confused myself about the order of the arguments. It turns out that the index is actually the down-pointing parameter and the element is the right-pointing one. So this comment was wrong, but while I was writing the function, I had it in that order the whole time. I had array, index, element, array, index, A, I, E. So when we changed this to a 2, it actually worked correctly because it inserted the value 0 at index 2, which changes the count, but not the leading zeros are invisible. So let's swap this around. I want to insert element number 2 at index 0. So now let's see what that gives us. That is the same number as this one. Oh, I made the same mistake again. Now, this is the index, so I want to change that to a 2. Now I've got it. So let's run that again, and this time we get a new number that we haven't seen yet. And here we have, so this is the stop bit, this is the length of the array, and this is the number 2 that we've inserted, and then that is the number 3 that was already in it. That seems to be working. Okay. Now, what happens if I insert a bigger number? So, for example, the number 7. This should recode the array. So once again, let's run that. We get a very different number. Okay, so the bit length is no longer 3, it is now 4. This is the stop bit, which means that the count is now these 4 bits. And it's correct. And then we have this. This is the number 7 that we inserted. And then we have the number 3 that was already in it. Now let's do the same thing, but in index 1. So we expect there to be a 3 and then a 7. So let's run that. Let's convert that. This is the stop bit. This is the length of the array, which is correct. And then we have the 3 followed by the 7. I think this is working. Now the only case that we haven't tested yet is this. You start with an empty array. And I'm going to insert at position 0 the number 7. So we should get an array with bit length 4 right at the start. So let's run that again and let's convert that number. So we do indeed get a bit length of 4, which means that 1, 2, 3, 4, this is the count. There is one element in this array that is correct, and that element is a 7. And now let's put that 7 at index 1. I now expect to see a 0 followed by the 7, and I expect the count to be 1, in other words, 2 elements. So let's see if that works. So this is the length of the array, this is the stop bit, and this is the count. Okay, so we have 2 elements now, and the first element is 0, and the next element is the 7. I think I'm reasonably happy now that this is working. Whew! Now, I said I wanted to write binary search in this video, but we won't be able to test our binary search function if we don't have a sorted array. So the next thing I'm going to do is to write a function that will convert a lazy sequence to an array, because we can easily create a lazy sequence from the input provided on the command line, and then we'll do binary search on the result of that. So let's say we have our lazy sequence. What do we need to do first? That's right, check if it's empty. Now, if it's not empty, then we can split it into head and tail. What are we going to do with that? Well, we can use a recursive call to convert the tail to an array, and then we would need to put the head in front, which we can do using the insert function that we just wrote. And the order of the arguments are the array, then the index, I forgot to put the connector here, and then the element that we want to add, which is the head of our sequence. Now, we always want to insert this at the start, so the index is always going to be 0. And the array that we pass in here is the result of a recursive call. And the thing that we want to pass into that is the tail. And now we can easily obtain the head and the tail by just calling the sequence. The lazy sequence ignores its input, so we put a 0 there. And now let me just rearrange this a little bit. And then we just need the declaration box to finish it off. And you know what? I'm going to reuse one of the 0 boxes just to save a little bit of space. Perfect. Now let's just add a comment to document what this function does. And now let's quickly test that. Let's just read standard input and split it at the commas. Then let's map over it to convert all of the strings to integers. And then let's call the function to convert that into an array. And of course we want to be able to inspect that array. So let's convert that integer to a string for output. And as I write this, I notice I put the wrong function here. So let me quickly fix that. And then let's run this. Let's run our program with an input of, let's say, 1, 2, 3. Each of these numbers is no more than 2 bits, plus the sign bit is 3 bits. So we expect an array with a bit length of 3 per element. So let's convert that number from decimal to binary and take a look. So here we have indeed the number 3, and then this is the count of elements. This is the stop bit. This is the count of elements, and it's a 2 because it's 1 less than 3, which is the number of elements that we actually have. Then the next 3 bits are this, which consists of a 0 sign bit and the number 1. And then we have the same thing with the number 2, and then a 0 bit and the number 3. So that seems to have worked. Now let's just quickly check that it works with larger numbers as well. I'm just going to put 2 numbers that are relatively large. 128 is a 1 with lots of zeros, and 127 is lots and lots of 1s. So let's convert this number from decimal to binary, and this is the bit length. So we have 1, 2, 4, 8, so 9. We have 9 bits per element. This is the stop bit. So 1, 2, 3, 4, 5, 6, 7, 8, 9. These 9 bits are the count, so the number of elements is 1 more than this, so it's 2. 9, that is indeed a 1 with lots of zeros. And then the rest is all 1s, except of course the sign bit is 0. Now I want to make absolutely sure that everything is working, so let's also try it with negative numbers. And we see that the bit length, which is this, is 2. There's only 2 bits per entry. And the first entry, this is the stop bit. And then this is the count, so it's 1 more than 1, so we have 2 elements. And then the first element is 0 but negated because the sign bit is 1. So that's the negative 1. And the next one is 1 negated, which is negative 2. So this is working correctly. Alright then, on to binary search. Now let's plan this properly. What are the inputs to this function? Well, there's definitely an array that we want to search for, and there is an element that we're looking for. Those are the inputs. And what do we want the function to output? I think I'm going to have it output two things. First of all, we want to know if the element was actually in the array. In other words, whether it was found. So that will be a boolean. It's always 0 for false or -1 for true. But then I also want to know the index in case it was found. But as you'll see in a second, we can also return a useful index even if it wasn't found. Since we're using binary search and assuming that the array is sorted, we will actually home in to the correct position where the element would have been. So we can return the correct index where the element should be inserted, if we should want to insert it and keep the array sorted. Okay, now let's think about what values we need to deal with. We will need to convert that array into the three values, the B, C, and E, where B is the bit length, the C is the count of elements in the array, and the D is the data block. But during the actual binary search algorithm, we also need to keep track of the bounds of the array that we're currently looking at. Initially, it'll be the whole array, but every time we have it, we want to keep track of the lower bound and the upper bound, which I'm going to call low and high. But remember that the binary search algorithm is an iterative thing, right? We start out with the entire array, but then we want to have the array and then basically kind of start over with that new bound. So the low and the high value are the only ones that keep changing. Now we need to use a recursive function to implement such an iterative process. So what do we need to pass into that recursive function? Well, at the very least, we need the array, we need the element that we're looking at, and we need the low and the high, which is already 4 values. And Funciton only allows up to 3 inputs to a function. But on top of that, I don't want to keep decoding the array into these 3 elements over and over. I want to do that once at the start of the binary search, because we're not modifying the array, we're only reading from it. So I'm going to try something that I haven't done before. I'm going to write a recursive lambda expression. So the iterative process needs to change only the low and the high value, and everything else it can just capture from outside of the lambda expression. So the lambda expression will need only 2 inputs, the low and the high value, and it'll only need 2 outputs, the found boolean and the index. A lambda expression can easily return 2 outputs, but as you know, we can only have 1 input per lambda expression, but we can stack lambda expressions inside of one another. So let's start by creating a double lambda expression to receive our low and high value. So if this lambda expression comes out here at the bottom, then this will be the first input, which is the low value, and this is the high value. And the outputs that we care about are the 2 outputs from the inner lambda expression. So we don't care about this one. We want the found boolean to come out of here, or to go into here, and the index to go into here. Now remember, the crux of the algorithm is to find the middle index between L and H, and then to update either L if it's too small or H if it's too large. If the element is not in the array, then eventually L and H will meet. So the first thing we should check is if L is equal to H, because then the element is not there. But we need the same condition on both of the outputs, so let's put a second box on the other output. Now the next thing I want to check is whether the element that is in between L and H is the element we're looking for. Now I want to continue the chain of conditions upwards. So I think I'm going to change that to L not equal to H, so that the true branch is the one way we can continue. So if L is actually equal to H, then we'll be on the false branch, and here we want to return 0, because the element was not found. And similarly here, I'm going to do the exact same thing, but this time if L is equal to H, we want to return the index where the element should have been inserted. So that can be either L or H. We know that they're equal, so it doesn't matter which one. Now let's introduce some variable names here. I'm going to say M for the index that is halfway between the low and the high index. And I'm going to say T for the element at that index. Let's move this to make some space. And now I want to check another condition. Specifically, I want to check whether the element that we're now looking at is in fact the element that we're looking for. So I would be tempted to ask if T is equal to E. But remember that we also need to check whether it's greater than or less than E in order to update the low and the high bounds correctly. So I'm actually going to start by checking if T is less than E. But again, since I want to keep stacking these conditions upwards, I'm going to change that to greater or equal to. so that if t is less than e, I'll be here. And what do I want to do here? I want to do the recursive call on the lambda expression using my updated values of L and H. Let's think about what they need to be. So if this is L and this is H, and we're looking at the middle element, and that element is too small, it means that all of the smaller elements will also be too small. So we should only update the low value to go to the middle, and the high value stays unchanged. So we want to pass M and then H. But actually, since t is strictly less than e, we know that m is not correct. So I can actually do m plus 1, which I'm going to do with the increment function. Okay, now the next condition is to check if t is less than or equal to e. So now we know that t is greater than e, which means that the middle element is too large. So everything after it will also be too large. So we want to update h to become the middle. And maybe I should decrement it, just like I incremented this one, because we know that t is too large, right? Well, actually, if we think of L and H as basically brackets around the area of the array that we're interested in, I think it makes sense for L to point at the first element, but H to point at the element after the last. As is often the case, it's most helpful here to think of L as an inclusive lower bound and H as an exclusive upper bound. So by setting the high value to m, we are already effectively saying that m is not included in the area of the array that we're looking at. Now, finally, what happens here? We now know that t is in fact equal to e, which means that we have found the element. So in this case, the found value should just be true, which is -1, and then the index that we want to return in that case is the index of the element that we found, and that would of course be m. Okay, now it's time to put in all of these comparison operations here. Let's start with the not equal to at the bottom. Now the thing about this comparison is that we also need it over here. So we actually need to take a copy of the output of the not equal function and pass it in through a wire crossing function. Now let's do the same thing with the t greater or equal to e. And remember that I can put the t and the e on either side. I can just change this to a less than or equal to if I want to swap them. So I'm just going to write this inside for now. And let's do the same thing here. Then let's join that up with the second occurrence. Okay, and then we need to do it a third time with the t less than or equal to e. Okay, so now let's think about the individual values that we want to return. We want to return a 0 here, we can easily write that. And same with the -1 up here, we can just write that. Now both of these conditions need the value t, and this is the only place where we need t. So I think I'm going to make this say t less than or equal to e, and I'm going to turn this around to have e less than or equal to t, so that I can put the t in between them. Now t is a value inside of the array. But remember, we've already deconstructed the array into its 3 constituent parts, including the bit length and the data block. And we already wrote this function earlier, which can take a data block and an index, and return the actual element, and do all the decoding of the sign bit for us. And the values we need in counterclockwise order is the bit length, the data block, and the index. So let's write an invocation to that function right here. Now the bit length of our array is not going to change, it's the b that we've obtained up here. Similarly, the data block is the d from here. And the index that we're looking at, well, we said that t is at the index m, so this should be m. Okay, now we need to invoke the lambda that we're currently writing. Actually, I think I'm going to do this one first. So we need a two-way nested lambda call. But let me just draw the first one first. And now let's think. What we want to pass into our question mark is the first output from that lambda expression, which means that this one here is going to be the second output. And we need that second output as well, because we want to pass that into here in the corresponding other question mark. So let's join that up now so that we don't forget. So now we know that we need the other lambda invocation box here. Now remember, the one that I just wrote second is the one that actually gets called first, because that's the one where we pass the lambda expression in. So the first argument L actually needs to go into here, and M needs to go into here, not the other way around. This one here is the second output of the first invocation, which we don't care about. We only need the lambda to invoke it the second time. And now let's put something very similar here. Now I can already see that this is going to be a nightmare to join up all of these values with where they need to go. But let's do the easy ones first. This lambda here, we can join that up with the other one. And we know that we need to ignore the second output of the first lambda here, so let's put the flag construct there. And the other second output needs to go down here. Oh Jesus, that means we need to go through at least 3 wires here. Now by putting this function here, we've already decided that t is going to be here and here. So let's quickly label the other sides with e's. Next, I want to connect the L's, M's, and H's. Let's start with this H here, which I can liberate with 2 additional wire crossing functions. And then there is this L here. Let's use 3 wire crossing functions to get that out of there. But now the big one is actually M, because remember that we need to calculate M from L and H. So let's start by getting this top M out of there. And now there is an M over here that we can connect that with. Then we have an M down here, which still needs to be incremented. And then there is another M down here, which I shouldn't forget about. So let's actually join those up right here. I want to rearrange that increment function slightly. Now let me zoom out a bit so that I can see more of the function, and then we can join up that M with the earlier one. Now it comes time to actually calculate M. Remember, to calculate the average of 2 values, you add them and divide by 2, and dividing by 2 can be achieved easiest by doing shift right 1 in Funciton. But as before, I'm going to express that as shift left -1. Now I'm gonna have to join up the e's eventually, so I think I'm going to do that now before I lose sight of it. And now we're basically only left with the L's and the H's. And I made a little mistake down here, because this is where the H comes out. I should have marked that with an arrow. So I need to connect all of the other occurrences of L and H with that. And I'm gonna start with the H, and for this L or H down here, I've decided I'm gonna use H. And now we need all the L's. And there seems to be only 3 of them, not as many as I thought. Now looking at this plus, we're adding these 2 values, so I think I can rearrange this to be a little bit more amenable. And now the last one that is still part of the lambda is the lambda itself. I need to pass the output of this into up here. Unfortunately, that only requires 2 more wire crossing functions. Of course, I'm taking another copy of the lambda expression here because we still need to actually call it. So let's think about what the actual function needs to do. We need to call the lambda in such a way that it will consider the entire array. So we want the lower bound to be 0, and we want the higher bound. Remember, we want that to be 1 more than the index of the last element. So that's actually just the count. So we're putting the lambda in here, so this is the first input to it, so that should be 0. And this is the second input, so we want that to be the count, the length of the array. And then this will be the first output, which we want to be the first output of the function, so this is where our dangling end goes. And this is the second output of our function, so we're going to leave that a dangling end as well. But we don't care about this output, so we're going to put a flag here to silence that. Now let's scroll up a bit and remind ourselves what we want the inputs to this function to be. Well, we get an array and an element, but then we don't actually need the array for any other purpose but to decode it into these 3 things. So I think I'm going to put the code to do that right here at the bottom. And we already know that we only need the C in 1 place, so we can join that up immediately. Now let me zoom out again so I can see more of the function. And then we can directly join up the B, D, and E because there's only 1 use of each of those. And now I think I can get rid of all of these notes that I wrote up here. And then finally, let's write a comment to document how this function works. The biggest function in the library definitely deserves the biggest comment. Okay, now let's write a program to test this function. We already have a program that can turn our input into an array, so we want to call the binary search function right here. And then counterclockwise from that, we're going to put the element that we're looking for. And then let's convert both of the outputs that we get into a string, and then let's concatenate those 2 strings with a comma in between. Now I can put any number here, let's just put 5 for now. And now let's run this. I'm really nervous because I don't expect this to work first try. But if we take a sequence consisting of the numbers 1 through 9, we expect a -1 because the element should be found, and it should be found at index 4. Okay, I do get a -1 and a 4. I just concatenated things up in the wrong order. Interesting. Fortunately, that's easy to fix because the only mistake was the direction of the output on this box. So if I just run this again, I do get what I expected. Now let's see what happens if I omit the 5, but I'm still looking for the 5. Indeed, I get 4, which is the index where it should go. If we have fewer elements here, now the 5 should be inserted at index 2. And that is indeed what I get. That is not what I expected. That entire complexity of the binary search function, first try. Now this video is probably gonna get long enough, so I won't bore you with more functions, but I will tell you what other functions I am planning to write. You see, now that we have a binary search function that can tell us where to insert an element, I can write a function that will turn a lazy sequence of integers in any order directly into a sorted array by simply inserting it in the correct place each time instead of always at the start. And conversely, we should probably also have a function that will turn an array back into a lazy sequence. So, I really hope that you enjoyed this fun odyssey. I promised you that I would finish with a binary search function, and I did. And we now have an entirely new library of arrays, where you can look up elements in constant time, where you can insert elements in the right place, where you can do binary search. I think this will be a lot more performant when dealing with collections of a large size. So, after this digression, let's continue with Advent of Code, shall we?